Welcome to Orbit Observer. It's lovely to have you here tonight, wherever you are right now. I hope you're somewhere soft. Maybe you're under a blanket that's just the right weight. Maybe there's a lamp still on across the room, throwing a little pool of warm light onto the wall, and you've been meaning to turn it off for the last 20 minutes, but you haven't quite gotten around to it. That's all right. Leave it on if you like. Or maybe you're on a train, watching the dark slide by, or curled on a couch with the day finally behind you. However you've arrived here, I'm glad you came. And before we drift off into the night, let me ask you the question I always like to ask. Where in the world are you watching from tonight? What time is it in your corner of the sky? I genuinely love reading these, so if you feel like leaving a little note before you fall asleep, tell me where you are. It's a strange and wonderful thing, all of us lying in different beds, in different cities, under the same handful of planets, listening to the same quiet voice. And if you enjoy these slow journeys through the night sky, a gentle like and a subscribe really do help this sleepy little channel keep going. I'm a small creator, and honestly, that quiet tap of support means more than I can say. To everyone already subscribed who comes back night after night, thank you. Truly, you're the reason there's a next one. Now here's my promise to you for tonight. And it's the same promise I always make. We're going to move slowly. There's no rush here, none at all. I'm not going to throw a wall of numbers at you or expect you to follow every twist. If your eyes get heavy, let them close. If you drift off before we reach the end, that's perfectly fine. That's the whole idea. And the rings will still be here, turning quietly when you wake. The ideas aren't going anywhere. We'll take them one at a time, gently, like turning the pages of a book you've already half fallen asleep inside. I'll try not to make this so interesting that it keeps you awake. Though I'll admit, sometimes I fail at that. But if I do, well, at least you'll have learned something beautiful before sleep finally takes you. A fair trade, I think. So, settle in. Get comfortable. Let your shoulders drop away from your ears. Tonight, we're going to drift all the way out to Saturn, and we're going to ask a question that sounds, at first, almost too simple to bother with. What is actually inside Saturn's rings? You already know the answer, don't you? Everybody does. Saturn has rings. They're made of ice. That's the fact you learned as a child, the fact on the poster. The fact that comes out whenever anyone says the word Saturn. Rings of ice. Tidy. Settled. Done. But I want to tell you something that I think will sit very strangely against that tidy little picture. Because hidden in those rings right now there is a ghost. Not a ghost in any spooky sense. Nothing to feel uneasy about as you're lying there. But there is genuinely no better word for it. There is a feature in Saturn's rings that is roughly the size of our entire planet, and it appears out of nowhere and then it fades away again. And it has been doing this for as long as we've been able to look, and after more than 40 years of staring at it, of pointing our finest spacecraft and our most powerful telescopes directly at it, nobody can fully explain what it is or why it's there. We call these things the spokes. Imagine the rings of Saturn as a vast, flat, spinning wheel. And now imagine, laid across that wheel, faint, dark streaks reaching outward from the inner edge toward the outer edge, exactly like the spokes on a bicycle wheel or the spokes on an old wooden wagon wheel. That's what they look like. Ghostly radial smudges painted across the brightest part of the rings, the part we call the B ring. And these spokes are not small. Some of them stretch as long as 20,000 kilometers from end to end, and around 2,000 kilometers wide. 20,000 kilometers. That's larger across than the Earth itself. A shadow the size of a world drawn onto the surface of the rings. And here's the part that I find almost impossible to hold in my head as I'm falling asleep. They form and they fade over minutes to hours, not over centuries, not over years, You could watch one appear in the time it takes you to make a cup of tea and watch it dissolve again before the tea's gone cold. They flicker into being, drift along with the rings as they turn, and then quietly vanish, as though someone had breathed onto a cold window and then watched the fog clear. We first saw them clearly in 1981. That was when the Voyager 2 spacecraft, sweeping past Saturn on its long, lonely journey out of the solar system, turned its cameras toward the rings and sent back images that genuinely puzzled the scientists waiting back on Earth. There they were, dark fingers laid across the ice, where no dark fingers should be. Features that didn't behave like anything anyone had a tidy box for. And here we are, more than 40 years later. And the honest truth is, we still don't entirely know what they are. We have ideas. Good ideas, even. We'll come back to them later, much later, once we've drifted through everything else, because the spokes deserve to be the last thing we look at, the way you save the most beautiful star in the sky for the moment right before you close your eyes. So I'm going to leave that little ghost hovering there for now, a question glowing quietly in the dark. We'll return to it, I promise, but I want you to hold on to the strangeness of it, because it tells you something. It tells you that the tidy little fact you learned as a child, rings of ice, true as it is hiding something much larger and much stranger underneath. The rings are not a quiet decoration hung in the sky 4.5 billion years ago and left alone ever since. They are not finished. They are not settled. They are, it turns out, an active, moving, changing, partly unexplained machine. And tonight, slowly, gently, we're going to take that machine apart and look at every piece of it. So let's go back to the beginning. Let's start where everyone starts, with the ice, because that part really is true. When we point our instruments at the rings and ask them what they're made of, the answer that comes back is, overwhelmingly, water ice, frozen water, the same stuff that forms in your freezer, the same stuff that crunches under your boots on a winter morning. The rings of Saturn are, to a very good approximation, an enormous field of frozen water drifting in orbit around a giant planet. But the moment you look closely, the simple fact starts doing something unexpected. It starts becoming a clue. When the Cassini spacecraft was at Saturn, it carried instruments that could read the light coming off the rings and decode what that light was telling us. One of these was an instrument called UVIS, which studied ultraviolet light, and another called VIMS, which read the rings in infrared, in colors just past the edge of what your eyes can see. And when scientists took the rainbow of light reflected by the rings and pulled it apart, the way you'd pull apart the colors in a soap bubble, they could read the chemical fingerprint hidden inside it. Every substance leaves its own signature in light, and the signature that came back again and again was water ice. Not just mostly, overwhelmingly. The numbers are extraordinary. The rings are something like 90 to 95% water ice and quite possibly more. Almost the entire thing, pure frozen water. The little bit that's left over is a small fraction of rocky, dusty material, the kind of grit we'd call silicate, plus a sprinkling of dark, carbon-rich dust, the cosmic equivalent of soot. A pinch of dirt in an ocean of ice. Now, I want you to sit with that because it's stranger than it sounds. The solar system is a dirty place. It's full of dust, tiny specks of dark material drifting between the planets, raining down constantly onto everything. Over millions and millions of years, anything sitting out there should slowly get coated in this dark, cosmic grime, the way an old book on a high shelf gathers a film of dust you don't even notice until you run your finger across it. Anything that's been out there for a very long time should be dirty, but Saturn's rings are clean. Almost impossibly clean. Pristine, gleaming, nearly pure white water ice. The way fresh snow looks in the first hour after it falls. before the world tramples it grey. And that single fact, that strange, stubborn cleanliness, is the first loose thread in the whole story. Because if the rings had been hanging there since the dawn of the solar system 4.5 billion years ago, they should be filthy by now, coated in soot, darkened almost beyond recognition. The fact that they're not, the fact that they're still so bright and so pure, whispers something that nobody expected. It whispers that the rings might be young, far, far younger than anyone once assumed. But we'll come back to that too. We're collecting threads tonight, you and I, gently, one at a time, and we'll weave them together later. For now, just hold on to this. The ice is real. And its very purity is the first hint that the rings are not what they seem. Now let's pull back and look at the shape of the thing, because the size of Saturn's rings is one of those facts that's so far outside everyday experience that your mind sort of slides right off it. So let's go slowly and let's find a way to actually feel it. The rings are enormous from side to side. The main bright rings, the ones you'd see through a small telescope from your back garden, stretch across something like 282,000 kilometers, edge to edge. That's nearly 3/4 of the distance from the Earth to the Moon. If you could somehow lay Saturn's rings down between us and the Moon, they'd reach most of the way across that gap. A flat, shimmering disk almost wide enough to bridge to the Moon. So they're vast. You'd expect them to be vast. That part fits the picture in your head. But here is the fact that breaks the picture. Here's the one that, the first time I really understood it, I had to stop and just stare at the wall for a moment. For all that width, all those hundreds of thousands of kilometers across, the main rings are typically only about 10 meters thick. 10 meters, top to bottom. The height of a few people standing on each other's shoulders. The height of a modest tree. In some places they thin down to even less, and near certain edges they bunch up a little thicker, but across most of that vast shining sheet, the rings are only around 10 meters from one face to the other. Now that number alone is hard to feel. 10 meters means nothing against 280,000 kilometers, because your mind can't hold both of those at once. So let's build a picture you can actually rest inside. Imagine you took a single, ordinary sheet of paper, just a piece of printer paper from a desk drawer, thin enough that you'd barely feel its weight in your hand. Now imagine you wanted to make a model of Saturn's rings out of that paper, keeping everything to scale, the width and the thinness, exactly as they really are. How wide would that sheet of paper have to be? It would have to be wider than a city. You'd have to take that one impossibly thin sheet of paper and stretch it out, keeping it just as thin until it spanned a couple of kilometers across. A sheet of paper as wide as a town and no thicker than paper. That's the true proportion of Saturn's rings. They are, relative to their width, far thinner than any sheet of paper you've ever held. They are very nearly two-dimensional, a shining flatness hanging in space, so thin that when we catch Saturn at just the right angle, edge on, the rings almost disappear from view entirely because there's so little of them in the up and down direction to catch the light. There's something gentle and almost dizzying about that, isn't there? This thing we picture as solid and substantial like a stone bracelet around the planet is really more like a vast, delicate film. A whisper of ice spread out across a space wider than worlds and barely thicker than the room you're lying in. And those rings aren't one smooth sheet. They're divided into bands, into separate rings nested inside one another, like the grooves on an old record, or like ripples spreading on a still pond and then frozen in place. Working our way outward from the planet, the first of the main rings is a faint, dim one we call the D ring, hugging close to Saturn itself, so faint you'd struggle to see it at all. Then comes the C ring, a little brighter, often called the crepe ring, for its sheer, gauzy, see-through quality, like a thin curtain. Then the B ring, and oh, the B ring. The B ring is the bright one, the dazzling one. the most massive and the most luminous of them all, the broad, gleaming heart of the whole system, and as it happens, the very band where our ghostly spokes like to appear. Then, just beyond the B ring, a gap, and then the A ring, the outer bright ring, holding secrets of its own that we'll get to. And past those main bright rings, the system grows faint and delicate. There's the narrow, twisted F ring, just outside the A ring, a strange, kinked, ever-changing thread. Then much farther out and far fainter, the G ring, a dim band of fine dust. And farther still the broad, ghostly E ring, so diffuse you could fly right through it and hardly know it was there, spread across an enormous volume of space. D, C, B, A, F, G, E, that's the order, outward from the planet. And if that order seems a little jumbled, not neatly alphabetical from the inside out, well, you've noticed something real, and there's a sweet little story behind it that we'll come to a bit later. For now, just let the names drift past you like stations on a slow night train. D, C, B, A, F, G, E. You don't need to memorize them. Let them wash over you. Now, we've talked about what the rings are made of, water ice, and we've talked about their impossible thinness, but there's another question hiding underneath, and it's a beautiful one. When we say the rings are made of ice, what does that actually look like up close? If you could somehow drift down into the rings slowly, gently, the way you might wade into shallow water, what would be floating all around you? And the answer is, it depends enormously on where you look, because the rings are not made of one kind of thing. They're made of countless separate pieces, all orbiting Saturn independently, each one on its own little path, and those pieces come in a staggering range of sizes. At the smallest end, there's dust, tiny grains of ice, finer than the powder of fresh snow, so small that thousands of them would fit across the width of a hair, a fine, glittering haze of frozen mist. And then working upward, the pieces get bigger. There are grains the size of sand, there are pebbles, the kind you'd skip across a pond, there are lumps the size of snowballs, the kind you'd pack together in your hands on a winter afternoon. There are blocks the size of boulders, and the bulk of all that mass, the great middle of the whole population, sits roughly in the range from centimeters to meters across, snowballs to boulders. That's most of what's there, if you went drifting through. A vast, slow-motion swarm of icy snowballs and frozen boulders, each one quietly orbiting, gently jostling its neighbors, the whole crowd of them drifting around the planet together. But it doesn't stop at boulders. Scattered among all those snowballs and stones, there are far larger pieces, chunks of ice the size of a house, the size of a building, and here and there, the size of a small mountain. Great icy crags tumbling slowly through the swarm, surrounded by the haze of smaller debris. So when you picture Saturn's rings now, I'd like you to let go of that smooth, solid poster image bracelet. Replace it, slowly, with something truer and far more wonderful. Picture a vast, flat, shining river of ice. A river made not of flowing water, but of countless separate pieces, from grains of frozen dust to drifting mountains, all moving together, all catching the distant sunlight, all turning in a slow, silent, endless circle around the great golden planet. There's no solid surface anywhere in there, nothing you could stand on, just an immense, gentle blizzard of ice stretched paper-thin across a space wider than worlds. And you might wonder, how on earth could we possibly know all that? How could we know there are snowballs and boulders and house-sized chunks out there when no one has ever flown a camera close enough to photograph a single ring particle? It's a lovely piece of cleverness, and it's the kind of thing that helps me drift off, this quiet ingenuity of people working out the unknowable. When the Cassini spacecraft was at Saturn, one of the things it would do is fly so that the rings passed directly between itself and a distant point, sometimes the Earth, sometimes a far-off star. And as the spacecraft sent its radio signals back home through the rings, or watched a star's light shining through them, the particles in the rings would interrupt that signal in tiny, telltale ways. Big particles block light and radio in one way. Small particles, fine dust, scatter and bend it in another. By reading exactly how the signal flickered and dimmed and shifted as the rings drifted across it, scientists could work backward and figure out what sizes of particles must have been there to cause that exact pattern. They never saw the snowballs directly. They read them the way you might read the shape of an unseen creature by the ripples it leaves on the surface of a dark pond. This technique even has a name, radio occultation, a fancy way of saying we watched the rings pass in front of something and learned their secrets from the shadows they cast. Isn't that a gentle kind of magic? To know the size of a boulder you'll never see, hundreds of millions of kilometers away by the way, it dimmed a whisper of radio light. So here's where we've come to, you and I, on this slow drift outward. We've taken the tidy little fact, rings of ice, and we've started to open it up. We've found that the ice is real, but startlingly pure, far too clean for something ancient, the first faint hint of a mystery. We've found that the rings are vast beyond imagining from side to side, and yet so thin they're nearly a shadow, a single sheet of paper stretched across a city. We've found that they're not one solid thing at all, but a slow blizzard of countless separate pieces, from grains of dust to drifting mountains, each one tracing its own quiet path around the planet. And hovering over all of it, still unexplained, still flickering, there's that ghost, the spokes, the Earth-sized shadows that appear and fade across the bright B-ring in minutes that Voyager 2 caught back in 1981 that we still cannot fully account for after all these years. We've only just begun, and already the simple picture is gone, replaced by something stranger and more alive. A young, paper-thin field of pure ice, full of moving pieces marked by a ghost no one understands. And we still haven't asked some of the biggest questions of all. We haven't asked how much all of this actually weighs, and why that number turned out to be such a shock. We haven't asked how old the rings really are, and why the answer might be younger than the dinosaurs. We haven't gone looking for the moons hiding inside the rings, the ones we can't even see directly, the ones we only know are there from the scars they carve. And we certainly haven't faced the strangest fact of all, the one I almost don't want to tell you, because it's a little sad, but it's true, and it's beautiful in its way. These rings are not forever. They are draining away, even now, falling into the planet, a little more with every second that passes. But all of that is still ahead of us, out there in the dark, waiting. For now, just rest with what we have. The ice, the thinness, the slow river of frozen stones, and the ghost hanging quietly over the brightest ring, keeping its secret a little longer. Let your breathing slow. There's no rush. The rings are still turning just as they have been all this time, and they'll keep turning while we drift on together, deeper into the strange and gentle machinery of Saturn's rings. So let me take you back, gently, to where this all begins. Not with the ghost, not yet. With something far more ordinary. With the idea you probably already carry in your head about what these rings are made of. If someone stopped you on the street and asked, you'd likely say ice. And you'd be right. But you'd also be missing almost everything interesting about the answer, because the question isn't just whether it's ice, it's how clean that ice is. And the cleanliness, it turns out, is the first real clue in the whole mystery. When the Cassini spacecraft turned its instruments on the rings, two of them in particular, the ultraviolet imaging spectrograph and the visual and infrared mapping spectrometer, the UVIS and the VIMS, it didn't just see a pale band of light. It read the fingerprint of the material itself. The way light bounces off a substance tells you what that substance is, almost like a chemical signature written in color. And what Cassini found, looking closely, was water ice. Not mostly ice with a lot of grime mixed in, not a dirty slush. Water ice making up something like 90 to 95% of the rings, and in many places even more than that. The rest, a thin scattering of rocky, silicate dust and dark carbon-rich material, a trace of dirt in a vast field of frozen water. Now you might hear that and think, well, of course, ice is ice. Why should the purity matter? But here's the quiet thing about it. Out there, in the space around Saturn, it is constantly snowing, not water snow, a fine, dark rain of micrometeoroids, tiny grains of dusty debris that drift through the solar system and pepper everything they touch. Over enormous stretches of time, that dark material settles onto surfaces and stains them. It dulls them. It mixes in. Anything left exposed for billions of years should be filthy by now, darkened and dimmed by all that infalling soot. And yet the rings are bright. They are almost startlingly clean. So clean that it raises a question that won't leave you alone once you've heard it. If the rings have been there since the very beginning, since Saturn itself formed 4.5 billion years ago, why aren't they dirty? Why are they still gleaming like fresh snow on a winter morning? That purity is the first whisper, the first hint that maybe these rings haven't been here all that long. We'll come back to that, hold on to it. But for now, let's stay with the ice itself, because there's more to picture here than just how clean it is. There's the matter of how it's arranged. And this is where the scale starts to bend your mind a little, in the soft, slow way that big numbers do when you're lying still in the dark. The rings spread out from Saturn in a great flat sheet, and if you measure all the way across from one side past the planet to the other, you're looking at something like 282,000 kilometers. That's the main bright rings, and even that is only part of it, because there are fainter, more diffuse rings reaching out far beyond. 282,000 kilometers. You could line up more than 20 Earths across that span and still have room to spare. It is a structure so wide it almost stops meaning anything, the way the distance to the horizon stops meaning anything when you stare at the sea. So you'd expect something that vast to be thick, deep, a great solid slab of ice surely to stretch so far. And here is where it becomes almost impossible to believe. The rings are about 10 meters thick. 10 meters? In the main rings, that's roughly it, top to bottom. In a few places near the edges, near where moons stir things up, it can swell to a few hundred meters. But across most of that immense span, you're looking at a sheet only about 10 meters from one face to the other. Let me try to give you a way to hold that, because the raw numbers don't quite land on their own. Imagine a single sheet of paper, thin, ordinary paper, the kind you could fold in your hand. Now imagine stretching that one sheet of paper across an entire city. Not a room, not a building, a whole city, edge to edge, with the paper staying flat and unbroken the whole way. That is the proportion we're talking about. The rings are, in their own way, more delicate than a sheet of paper, spread across a distance you couldn't walk in a lifetime. A vast, gleaming, almost two-dimensional thing hanging in space, so thin that when we see it perfectly edge-on from Earth, it very nearly disappears. And it isn't one smooth sheet either. From the planet outward, the rings sort themselves into bands, and they're named, oddly enough, not by where they sit, but by the order in which they were found. So as you move outward, you pass the D ring first, closest in, faint and dim. Then the C ring, then the B ring, the brightest and most massive of them all, the one where our ghost lives, then the A ring, and further out, the narrow F ring, then the wispy G ring, and finally the broad, diffuse E ring, spread thin across an enormous region of space. D, C, B, A, F, G, E. Not in order, never quite in order. A little jumbled, the way real history always is when discovery comes before tidiness. Now picture yourself drifting down toward that sheet, slowly, the way you might sink into sleep. From a distance it looks solid, smooth, like polished metal, or the surface of a frozen lake seen from a high window, but that smoothness is a kind of gentle lie, a trick of distance, because the rings are not solid at all. They never were, they couldn't be. What they actually are, when you get close enough to see, is countless separate pieces, not a single sheet of ice, but an uncountable swarm of individual chunks, each one orbiting Saturn on its own, each one minding its own quiet path, all of them together moving in such graceful order that from far away they blur into the appearance of something whole. And those pieces come in every size you can imagine. Cassini studied them in part by a clever trick. The spacecraft would send a radio signal back toward Earth straight through the rings, and by watching how that signal dimmed and shifted as it passed through, scientists could work out the sizes of the particles it was passing between. It's a little like learning the size of stones in a riverbed by listening to how the water moves over them. They called it radio occultation, the slow reading of the rings by the light and the radio waves that filtered through. What they found was a whole population, a whole crowd of frozen bodies. At the smallest end, fine grains of dust, no bigger than specks, particles so tiny you'd need a microscope to catch a single one. And then, scaling up from there, snowballs, pieces the size of a fist, the size of a melon, the size of a beach ball. The bulk of it, the great mass of the rings, sits somewhere in that middle range, particles from about a centimeter across up to a meter or so. Snowballs and boulders drifting along together. But it doesn't stop at boulders. Mixed in among the snowballs are far bigger things. Chunks the size of a car, the size of a house. And here and there, scattered through the swarm, pieces as large as a small mountain, great icy mountains tumbling silently along their orbits, surrounded by clouds of their smaller cousins. So when you imagine the rings now, set aside the polished sheet. Picture instead a slow, endless river of ice, dust like fine snow drifting in the gaps, snowballs and boulders by the trillion, and every so often a frozen mountain rolling past in the dark, gleaming faintly in the distant sun. All of it moving, all of it turning, each piece on its own quiet path, none of them touching the next, except in the gentlest, rarest brushes. A flock, a swarm, a crowd of frozen stones the width of 20 Earths and the thickness of a single page. And the strangest part, the part worth carrying down into sleep with you, is that this isn't chaos. It looks like it should be a jumble, a mess of debris. But it isn't. Every piece, the dust grain and the mountain alike, obeys the same simple law, the same gentle pull, and out of that one law comes all the order you see, the bands, the brightness, the flat and shining sheet. A trillion separate things behaving together like one. We've felt how clean the ice is, we've felt how impossibly thin the rings are, paper across a city. We've drifted down among the snowballs and the mountains and seen that the solid sheet was never solid at all. And still the biggest surprises are waiting, because soon we're going to ask how much all of this weighs, every last grain and boulder of it, and the answer, when Cassini finally measured it, was so small it left scientists genuinely stunned. But before we get to the weigh-in, let's spend a quiet moment with the rings' names, because even the way we label them holds a little surprise. You might expect the rings to be named in the order they sit, outward from Saturn, a tidy alphabetical procession. They aren't. The rings are named in the order they were discovered, and since astronomers found the brightest ones first, and the fainter, harder to see ones later, the labels ended up scattered across the sky in a way that has puzzled generations of students. Moving outward from Saturn, the order goes D, then C, then B, then A, and then farther out, F, then G, then E. The D ring hugs Saturn most closely, faint and gossamer, barely visible. Then comes the C ring, broader and slightly brighter, sometimes called the crepe ring, for its translucent, gauzy quality. Then the B ring, the one that blazes when you point almost any telescope at Saturn, the ring that made Galileo reach for his quill and stare in baffled wonder. Then the A ring, broad and beautiful, separated from the B ring by a gap we'll come back to in a moment. And then the fainter outer rings, the F ring, a narrow, twisting strand just beyond the A, and the G and E rings even farther out, so faint they barely register in ordinary light. The B ring is the heart of the system. It is the brightest. It is the most massive. When you see Saturn in a photograph, when the rings leap out at you in all their glory, it is mostly the B ring you are seeing. It is also, as it turns out, the most mysterious, the one whose deep interior Cassini could not fully read, the one whose structure still holds questions. But we'll get to that. For now, just hold the B ring in mind as the giant of the family. Bright, thick with material, the ring that anchors everything. And between the B ring and the A ring, there is the gap. It is called the Cassini division, named for the Italian-French astronomer Giovanni Cassini, who first observed it in 1675. From Earth it looks like a clean, dark stripe, a ruler-straight void separating the two brightest bands. And for a long time, people thought it was simply empty. A gap, a nothing. It isn't nothing. The Cassini division is about 4,700 kilometers across, 4,700 kilometers wider than the continental United States from the west coast to roughly Chicago. And it does contain material, sparse material, darker and dustier than the bright rings on either side, but real particles, real ice, still there. The reason it looks empty is that most of the material has been cleared out, not by a random accident, but by something much more elegant, a mathematical resonance. The moon Mimas is responsible for this. Mimas, one of Saturn's smaller moons, a battered little world with a crater so enormous it makes Mimas look uncannily like the Death Star from a certain famous film. Mimas orbits Saturn farther out, beyond the rings, minding its own business. And its gravity, though modest, has had an enormous effect on the ring material inside the Cassini division. Here is how. A particle sitting right in the middle of the Cassini division orbits Saturn at a very specific speed. At that distance from Saturn, a particle completes exactly 2 orbits for every single orbit Mimas completes. 2 to 1, a 2 to 1 resonance. And this means that every time the particle loops back around to the same point in space, Mimas is there too. Or more precisely, Mimas is always at the same relative position each time the particle passes. Every 2 orbits, the particle gets a small gravitational tug from Mimas in exactly the same direction, and then 2 orbits later, another tug, and another, and another. Individually, each tug is tiny, but they accumulate. They add up, orbit after orbit, the same little nudge, always pushing in the same direction. And over millions of years, those nudges grow into something powerful enough to fling particles out of the division entirely. It is like pushing a child on a swing, always at the same moment in the swing's arc, gently at first, then higher and higher. The resonance is the timing, the patience, the accumulation. And the Cassini division is the result, a gap 4,700 kilometers wide, cleared by the persistent arithmetic of gravity. There are other resonances elsewhere in the rings too, other gaps and structures carved by other moons, the whole ring system sculpted by these invisible mathematical relationships. But the Cassini division is the most dramatic, and it bears reminding yourself what looks like emptiness from Earth is actually a carefully swept corridor, kept clean by a moon that orbits millions of kilometers away. Now, about whether the rings themselves are solid. You already know intuitively that they can't be. We've drifted through them and found a swarm of particles, each on its own orbit. But the question of whether the rings could be solid was once a genuine scientific puzzle, and the person who settled it did so not with a telescope, but with mathematics alone, sitting at a desk more than 160 years ago. His name was James Clerk Maxwell, and in 1859 he turned his attention to Saturn's rings for a very specific reason: the Adams Prize, a prestigious competition set by Cambridge University asking entrants to investigate the stability of the ring system. Maxwell was already one of the most gifted mathematical physicists alive, the same man who would later unify electricity, magnetism, and light into 4 elegant equations that still anchor all of modern physics. He brought that same precision to Saturn. He began by asking a simple question. If the rings were a single solid disk, would they be stable? Could they orbit Saturn safely for billions of years without breaking apart? His mathematics said no, definitively, clearly no. A solid ring, Maxwell showed, would be gravitationally unstable. Saturn's gravity is not perfectly uniform, and a solid ring, even if you could somehow build one, would be tugged unevenly, would wobble, and would eventually spiral apart or shatter. No solid structure could survive in that orbital environment. He then tested the possibility of a liquid ring, a continuous fluid band. Again, his equations ruled it out. A liquid ring would ripple and fragment under its own tidal forces. The only configuration that could remain stable, that could persist, that could survive the gravitational environment of Saturn, was one made of countless separate independent particles, each in its own orbit. A swarm. Maxwell won the Adams Prize for this analysis in 1859, and it was a triumph of pure reasoning. He had never set foot near a telescope for this work, had looked at no ring particle directly. He had sat with equations and deduced, with absolute mathematical confidence, what the rings had to be. The observational confirmation came later, in 1895, from the astronomer James Keeler, who measured the Doppler shift of light coming from different parts of the rings. In other words, he measured how fast the ring material was actually moving, and the result matched Kepler's laws exactly, the same laws that govern planets orbiting the Sun. The inner edge of the rings moved faster than the outer edge, as any independently orbiting object must. Tighter orbits are faster orbits. A solid disk would have rotated like a rigid wheel, the outer edge sweeping faster than the inner. The rings did the opposite. Inner fast, outer slow. Every piece on its own Keplerian path. Maxwell's prediction confirmed 36 years later by starlight and a spectroscope. But why then don't the particles simply clump back together? If you have 1 trillion snowballs and ice boulders all orbiting Saturn, why don't they slowly accumulate, gravity pulling them toward each other, eventually reassembling into a moon or two? The answer is the Roche limit. Every large body, a planet, a star, anything massive enough, has a boundary around it called the Roche limit, named for the French astronomer Édouard Roche, who calculated it in 1848. Inside this boundary, the tidal forces from the central body are so powerful that they overcome the self-gravity of any loose accumulation of material. Tidal forces in this context means the difference in gravitational pull across a small body. The near side of a clump of particles is pulled towards Saturn more strongly than the far side, and that difference in pull, that stretching, tends to pull the clump apart. If the clump is small enough and loose enough, it can't hold itself together against that differential. It fragments. The pieces scatter. Saturn's rings sit right inside Saturn's Roche limit. Any loose collection of particles there, any proto-moon trying to grow, any boulder accumulating smaller debris, gets pulled apart before it can hold itself together. The rings exist not despite Saturn's gravity, but because of it. Saturn's tidal forces are what prevent the material from reassembling into moons And so the rings persist, particle by particle, each piece alone in its orbit, unable to join with its neighbors except in the most temporary, glancing way. It is worth pausing on this for a moment because it is a beautiful inversion of how we usually think about gravity. Usually we think of gravity as the great assembler, the force that gathers gas clouds into stars, dust into planets, rocks into mountains. And outside the Roche limit, that is exactly what it does. Saturn's moons sit beyond the Roche limit, and they are spheres pulled into roundness by their own self-gravity. But inside the Roche limit, Saturn's tidal gravity is the great disassembler, the force that keeps the rings from becoming anything else. The ring particles are held in permanent suspension, prevented from becoming a moon too deep inside Saturn's gravitational embrace. Now we come to the question of weight. For all the beauty of the rings, for all the structures and patterns, one thing scientists had never been able to measure precisely, not from Earth, not from the early Saturn flybys, not even from Cassini's years in orbit, was how much the rings actually weighed, their total mass. This turned out to be an extraordinarily difficult number to pin down because the rings scatter and absorb radio waves in complex ways, and their own dynamics made indirect measurements uncertain. The answer came at the very end. In the final months of the Cassini mission, the spacecraft was directed into a series of orbits no probe had ever attempted before. 22 dives, 22 times, Cassini threaded the gap between the innermost edge of the D ring and the top of Saturn's atmosphere, passing through a region of space only about 2,000 kilometers wide, closer to Saturn than any spacecraft had ever been. The team called it the grand finale, and on those passes, Cassini measured the gravitational pull of the rings directly. The rings' mass tugged on the spacecraft very slightly as Cassini flew by, and those tiny tugs, felt as minute changes in the probe's trajectory, tracked precisely by radio signals from Earth, allowed scientists to calculate exactly how much material was there. The answer, published in 2019 by a team led by Luciano Ies, was startling. The rings weigh roughly 1.5 times 10 to the 19th kilograms, 1.5 times 10 to the power of 19. Written out fully, that is 15 million trillion kilograms. It sounds enormous, but in planetary terms it is tiny. It is approximately 40% of the mass of Mimas, the same Mimas whose resonance carved the Cassini division. Mimas, which is already one of Saturn's smaller moons, barely 400 kilometers across. The rings, spread across nearly 300,000 kilometers, contain less than half the mass of that small, lumpy, battered little moon. Put another way, if you gathered all of Saturn's rings, all of it, the B ring, the A ring, the C ring, every dust grain, every snowball, every mountain-sized chunk drifting through the system, and squeezed it together, you would end up with something smaller than Mimas. You could tuck the entire ring system inside a moon that fits comfortably inside the borders of France. And Saturn itself is almost 760 times the diameter of Earth. The rings, for all their spectacle, for all their blinding brightness and planetary scale spread, are a whisper. A vanishingly thin and low-mass whisper stretched across a canvas nearly as wide as the distance from the Earth to the Moon. This small mass, it turns out, is not just an interesting fact about the rings. It is one of the most important clues to their age, and the age of Saturn's rings is one of the great live debates in planetary science right now. Here is the logic, laid out slowly because it is worth understanding completely. Imagine the rings as a white carpet, a very clean, very white carpet, spread across the solar system. The solar system is not a clean place. Space is full of debris, micrometeorites, tiny dust particles from asteroid collisions, and cometary tails drifting slowly through the void. These particles rain down on the rings constantly, all the time, in an invisible, slow drizzle from above and below. And when they hit the ring particles, which are mostly bright, white, nearly pristine water ice, they leave a dark stain. Carbon, silicates, rock, the dark material of the impactor, smearing itself into the surface of the ice grain. Over time, this darkening accumulates. The older the rings, the more time they've had to collect this dark rain from space, and the darker they become. Old rings are dirty rings, new rings are clean rings. Saturn's rings are very clean. That purity we talked about earlier, the 90 to 95% water ice, that near-pristine composition measured by Cassini's ultraviolet imaging spectrograph and its visual and infrared mapping spectrometer. That cleanliness is itself a timestamp. But here is where the mass matters. A more massive ring system can absorb more impactors without changing color very much, because the infalling dark material is diluted across a greater volume of ice. A low-mass ring system darkens faster. It has less ice to dilute the dirt, so a low-mass clean ring system implies either a very recent origin, the rings simply haven't had time to get dirty, or some mechanism that is actively cleaning them, keeping them white, despite the passage of time. Cassini's measurements pointed strongly toward the first explanation. The mass was low and the composition was clean, and when scientists modeled the rate of micrometeoroid pollution, led by Kempf and colleagues in a study published in Science Advances in 2023, they concluded that the rings have likely existed for somewhere between 100 million and 400 million years, perhaps as young as 100 million years, perhaps as old as 400 million, with considerable uncertainty in between, but even the outer edge of that range is only 400 million years. The solar system is 4.5 billion years old. The rings, if this analysis is correct, formed in only the last 10% of solar system history, perhaps the last 6 or 8%, and those are dates the dinosaurs would have recognized. Sauropods, long-necked giants like Brachiosaurus, were already walking the Earth 150 million years ago. Tyrannosaurus rex lived around 66 to 68 million years ago. Depending on exactly when the rings formed, they may have appeared while Mesozoic dinosaurs still walked the Earth, or even after many of them had already been walking for millions of years. Saturn existed for billions of years without its rings. Then, relatively recently, in geological terms, the rings appeared. Saturn woke up one day and had rings, cosmically speaking. They are not the ancient, eternal decoration we might have imagined. Now, before we go further, because this is an honest exploration, we need to sit with the fact that this conclusion, seen as compelling as it is, as strongly as the evidence points toward it, is not unanimously accepted. Science rarely moves in clean, unanimous steps, and the youth of Saturn's rings is a live debate. In 2024, a team of researchers with Aurélien Krieger among those contributing to the dissenting view proposed an alternative explanation for the ring's apparent youth. The argument goes roughly like this. When a micrometeorite slams into ring particles, the collision doesn't just leave a dark smear on the ice. The impact vaporizes material, both from the impactor and from the ring itself, creating a cloud of gas and plasma. And this cloud, the argument suggests, might carry the dark pollutants away with it rather than depositing them into the ring. If the pollution is being regularly ejected from the system rather than accumulating, the rings could remain bright and clean even if they are much older than the pollution model suggests. The rings could, in other words, be self-cleaning. The apparent brightness would not be a sign of youth, but of a cleaning mechanism operating continuously for billions of years. This is a serious scientific proposal, and it has not been dismissed. The question of exactly what happens to micrometeorite debris at the moment of a high-speed impact into a ring particle is genuinely hard to model and genuinely hard to measure directly. The 2024 paper opened the door back up to the possibility of an ancient ring system, billions of years old, merely maintaining its brightness through a poorly understood self-cleaning process. So where does this leave us? The current scientific consensus leans toward youth, the mass measurement from Cassini, the composition measurement, the pollution rate modeling from Kempf and colleagues. These converge toward a young ring system, but the 2024 counter-argument is real, and the debate is genuinely alive. If you go to sleep tonight thinking the rings are between 100 and 400 million years old, you are in good company with the majority of planetary scientists. But hold that conclusion a little loosely, because the people who study these things for a living are still arguing about it, and that is exactly as it should be. What scientists do agree on, regardless of which side of the age debate they fall on, is that if the rings are young, then something made them. Something happened relatively recently in Saturn's neighborhood, something dramatic and violent that shredded an enormous amount of icy material and spread it into orbit around the planet. And the leading candidate for what that something was is a story that is, in its own quiet way, haunting. Saturn, as you may know, is tilted. Its rotational axis doesn't point straight up and down relative to its orbit around the Sun. It leans about 27 degrees off vertical, like a spinning top that has been nudged. This tilt is, in itself, something that needed explaining, because the dominant theories of how the solar system formed suggested Saturn should be tilted much less. A team led by Jack Wisdom at MIT, publishing in the journal Science in 2022, offered an elegant and deeply strange explanation that ties Saturn's tilt directly to the origin of its rings. Their hypothesis centers on a moon that no longer exists. They call it Chrysalis. Chrysalis, in their model, was once a mid-sized moon of Saturn, perhaps comparable in size to Iapetus, one of Saturn's surviving moons. A body perhaps 1,000 kilometers or more across, a world in its own right. Chrysalis orbited Saturn in the outer reaches of the moon system, a normal, stable moon going about its quiet business. But over time, and this is the key part, Chrysalis's orbit became gravitationally entangled with Saturn's precession, the slow wobble of Saturn's rotational axis, as it is pulled by the gravity of other planets, particularly Neptune. This gravitational entanglement, a kind of resonance between Chrysalis's orbit and the rhythm of Saturn's axial wobble, slowly dragged Saturn's tilt higher and higher, pulling the planet's axis toward its current 27-degree lean. And then, approximately 100 to 200 million years ago, Chrysalis's orbit became unstable. The moon wandered too close to Saturn, dipping inside the Roche limit, that boundary we discussed where tidal forces overcome self-gravity, and Saturn's tides tore Chrysalis apart. The moon that had spent billions of years nudging Saturn's tilt was destroyed, shredded into fragments, and those fragments scattered into orbit around Saturn, colliding and grinding down into smaller and smaller pieces, eventually spreading into the ring system we see today. In this telling, Saturn's rings are made from the bones of a lost moon. And that same moon's destruction also released Saturn's axis from the resonance that had been tilting it, leaving the planet leaning at its current angle, the tilt now frozen in place without Chrysalis to maintain it. It is a deeply satisfying story, because one event, one lost moon, explaining both the rings and the tilt. And the numbers align. The timing of a disruption 100 to 200 million years ago matches comfortably with the pollution-based age estimates. Chrysalis is not confirmed. It is a hypothesis, a model, a proposed explanation for a set of observations. The moon itself is gone, and by definition we cannot observe its destruction directly. But the hypothesis fits the evidence with a kind of quiet elegance, and Wisdom and colleagues presented it with the mathematical rigor it deserved. So when you look at Saturn's rings and feel that they are eternal, feel that they have always been there and always will be, let yourself gently revise that feeling. There was a time, not long ago in cosmic terms, when Saturn hung in the sky, with no rings at all. Then a moon strayed too close, and Saturn became Saturn. But the story of what lives inside those rings, what happens moment to moment right now in the swarm of ice and dust, is still unfolding. We have given the rings their age, or our best guess at it. We have given them their origin, or the most plausible story we have. Now let's go deeper into the machine, because the rings are not static. They are not frozen in their current configuration, a snapshot preserved in time. They are sculpted continuously by bodies moving through them. And the sculptors include some objects so small you cannot see them directly. You only know they are there because of the shapes they leave behind. Hidden inside the A-ring, the second brightest, the one sitting just beyond the Cassini division, are hundreds of moonlets, not the great shepherding moons we'll come to in a moment. Smaller than that, much smaller, bodies tens of meters across, maybe 100 meters, maybe a few hundred meters, the size of a city block or a football stadium or a modest hill. Too small to image directly from any spacecraft we have built, too small to see as anything but a point of light, even at Cassini's closest approaches. You would not know they were there except for one thing: they leave wakes. When a moonlet this size moves through the ring, its gravity pulls on the ice particles nearby. The particles in front of it are dragged back slightly, the particles behind it are flung forward slightly, the ones to the sides are tugged inward and then outward in a complex gravitational dance. And the pattern this creates, worked out precisely by the mathematics of orbital dynamics, is a double wake, a branching, diverging shape that spreads out ahead of and behind the moonlet as it moves through the ring. Like the bow wave of a ship, except in two directions, fore and aft, spreading in a graceful, diverging plume. The shape, when Cassini finally photographed it, looked unmistakably like a propeller. And so these features are called propellers. The moonlet itself is invisible, but the propeller wake it carves is real, measurable, photographable. You see the scar without seeing the cause. Matthew Tiscarino at the Space Science Institute and colleagues identified these features first in 2006, publishing in Nature. They found hundreds of them in the A-ring, a whole population of unseen bodies betraying themselves through the shapes they cut into the ice. And the propellers varied in size, some small, some larger, some large enough to leave wakes that spanned hundreds of kilometers. Enormous trails for a hidden body barely the size of a neighborhood. A handful of the larger propellers, the ones leaving the most prominent wakes, were tracked over years of Cassini observations, their positions logged orbit after orbit. And because they were tracked as individuals, these specific invisible moonlets followed over time. Scientists gave them names. They named them after pioneers of flight. There is Blériot, named for Louis Blériot, who in 1909 made the first crossing of the English Channel by airplane. There is Earhart, named for Amelia Earhart. There is Santos Dumont, named for Alberto Santos Dumont, the Brazilian aviation pioneer. These named propellers, Blériot and Earhart and Santos Dumont and a few others, became some of the most closely watched objects in the solar system. Not because of what they are exactly, but because of what watching them tells us. Tracking a moonlet in a ring over years reveals how its orbit changes over time, how it interacts with the surrounding particles, how a small body in a dense disk of material drifts and is nudged. And this is, as it happens, a model in miniature for something much larger, the formation of planets around young stars. When a star is young, it is surrounded by a disk of gas and dust, and planets grow inside that disk by accumulating material. But how exactly a growing planet interacts with the disk, how it clears gaps and opens spirals and migrates inward or outward as it grows, these are things that are extremely difficult to observe directly, because young planet-forming systems are far away, and the planets themselves are embedded in the disk and nearly impossible to distinguish from the surrounding gas. Saturn's rings with their trackable propeller moonlets offer something rare, a natural laboratory right here in our solar system where you can watch a small body in a disk, track how it moves, measure how the disk responds. Blériot and Earhart, orbiting in the A-ring, are proxies for something larger, the story of how planets are born. And so the A-ring holds within it this extraordinary miniature, these invisible architects, moonlets betrayed only by their wakes, named for the pioneers of human flight. But the A-ring is not the only place where moons shape the rings. Step a little inward, toward the edges of the great gaps, and you find something different. Not hidden moonlets you can only infer. Actual moons, small, strange shaped, and busy. Inside the Encke Gap, a clearing in the outer A-ring, roughly 325 kilometers wide, orbits a moon called Pan. Pan is small, only about 28 kilometers across, at its widest. And if you were able to hold it in your hand, which you obviously cannot, you would notice immediately that it has a very unusual shape. It does not look like a potato, or a pebble, or any of the rough, irregular lumps we typically picture when we imagine small moons. Pan looks, to be quite honest, like a ravioli, or perhaps a flying saucer, if you are in a different mood. It has a distinct equatorial ridge, a thick belt running around its middle, giving it that flattened, disk with a bulge appearance that planetary scientists find quietly delightful. The same is true of Atlas, another small moon that orbits just outside the A-ring's outer edge, shepherding material there. Atlas, too, has this ravioli quality, this flying saucer silhouette, and the reason for the shape is itself a story about how the rings work. Both Pan and Atlas have accumulated ring material around their equators over time. As they orbit through or beside the ring plane, fine particles from the rings gradually stick to them, building up that central bulge, giving them their distinctive profiles. They are moons that have eaten the rings in a small way, and where the evidence of it? They are shaped by the very environment they are shaping, because that is what Pan does inside the Encke Gap. It does not just sit there passively in a clearing it happened to find. It is actively maintaining that gap. Its gravity, as it orbits, sweeps material away from the gap's lanes, preventing the Encke Gap from closing up and filling back in with ring particles. Without Pan, the gap would likely not exist, or would look very different. Pan carved its own home, and it keeps carving it, orbit after orbit. But here is where it gets genuinely striking. The edges of the Encke Gap are not smooth. They are not clean walls of ice. They are corrugated, rippled, shaped into a series of waves by Pan's gravitational pull. And the same is true, even more dramatically, for the other great shepherd moon sitting in its own gap, further inward, Daphnis. Daphnis orbits inside the Keeler Gap, a narrower clearing, and Daphnis is even smaller than Pan, only about 8 kilometers across. A tiny thing by any measure. And yet, the edges of the Keeler Gap, under Daphnis's influence, are not merely rippled. They are raised into vertical waves, great undulating ridges of ring material standing hundreds of meters above and below the average ring plane. Hundreds of meters, in a ring that overall is only about 10 meters thick. The waves are, in places, taller than the ring itself is thick. The math of that seems almost wrong until you sit with it for a moment. The ring, seen from the side, is extraordinarily flat. But near Daphnis, the edges of the Keeler Gap are folded into towering pleats, and those waves cast shadows. This was one of the most arresting images to come back from the Cassini mission during Saturn's 2009 equinox. The moment when the sun crossed the ring plane, striking the rings at an extremely low angle like late afternoon light raking across a field and throwing every small bump and ridge into long, dramatic shadow. In those images, the waves at the Keeler Gap's edges cast shadows that you could measure in hundreds of meters, A moon 8 kilometers across, orbiting in a gap, raising waves in a sheet of ice 10 meters thick, throwing shadows hundreds of meters long. The scale comparisons keep bending the mind, every single one of them. It is worth taking a breath here, if you are still awake, and simply holding that picture. Saturn's rings, which from a distance look smooth and luminous and perfectly drawn, are on closer inspection an endlessly active surface. Waves rising and falling at gap edges, ravioli-shaped moons sweeping their lanes clean, hundreds of propeller wakes spread across the A-ring, each one the signature of a moonlet you cannot directly see. The rings are not static, they are not a frozen decoration. They are in constant, complex, gravitational conversation with every piece of material and every moon within and around them. And then there is the F-ring. The F-ring sits just outside the A-ring's outer edge, and it is, in the taxonomy of Saturn's rings, something of a category of its own. The main rings, the D, C, B, and A, are broad, relatively stable, and dense. The F-ring is none of those things. It is narrow, only a few hundred kilometers wide at most. It is relatively sparse, and it is, without question, the most dynamic, most rapidly changing, most actively chaotic part of the entire ring system. The F-ring is watched over, that is the right word, by two shepherd moons, Prometheus and Pandora. Prometheus orbits just inside the F-ring's inner edge. Pandora orbits just outside the outer edge. The two of them together act as gravitational fences, keeping the F-ring's material from spreading too far inward or outward, corralling the ring into its narrow lane. That is the textbook description of the F-ring, and it is accurate as far as it goes, but it does not quite capture what is actually happening there. Because Prometheus, in particular, does not simply orbit quietly beside the ring, it is an active disruptor. Prometheus follows a slightly elliptical orbit, which means that once every revolution, roughly every 15 hours, it dips slightly closer to the F-ring. And when it does, its gravity reaches into the ring and pulls out material, drawing long, thin streamers of particles toward itself before they fall back. These streamers become kinks, braided structures, channels, what scientists working with Cassini data called streamer channels. Each time Prometheus passes close, it pulls a new streamer out of the ring material, and the previous streamer from the orbit before has by then been sheared by the differential orbital speeds into a faint, curved trail. The result is that the F-ring, over time, is not a single, clean strand, but a complex, braided, ever-changing braid of strands and channels and kinks. Different parts of it are being disturbed at different times. A quiet stretch of ring becomes a kink as Prometheus approaches. The kink elongates into a streamer. The streamer curves into a channel. The channel fades and is replaced. The F-ring in Cassini's images from year to year looks recognizably like a ring, and yet the details are never the same twice. New structures are always forming, old ones are always disappearing. If the main rings are a slow, stately system, the F-ring is jazz. There is something a little poignant about this, actually. The F-ring sits at the very outer edge of the main ring complex, narrow and restless, constantly being kneaded by Prometheus, never quite settling into a stable shape. It is the most alive part of the most alive ring system in the solar system. Now, let us go somewhere else entirely for a moment, not outward from the rings, not inward, but inward in a different sense. Into the rings themselves, into their structure. Because there is something remarkable about the way the rings are organized at fine scales that goes beyond what we can see directly, and it has to do with sound, or rather, with the mathematical equivalent of sound. Spread through the rings, particularly through the A-ring and parts of the B-ring, are patterns that planetary scientists call density waves and bending waves. These are not random variations in the rings. They are organized, rhythmic structures, spiraling outward or inward, repeating with remarkable regularity. And if you were somehow able to look down at the ring from above with impossibly fine resolution, they would look, as scientists who work on this have described it, like the grooves on a vinyl record, tightly spaced, spiraling, wave after wave after wave. These waves are generated by orbital resonances with Saturn's moons. The moons pull on the ring particles, and where a moon's orbital period has a simple ratio with the ring particle's orbital period, where a particle orbits twice, or 3 times, or 4 times for every one orbit of a moon. The repeated gravitational tugs build up and drive a wave through the ring material, the way a finger dragged across a drum skin drives a ripple outward. Different moons drive different waves at different locations. The result is that the rings are threaded throughout with these wave patterns, each one a record of a moon's gravitational influence. And here is where it gets genuinely extraordinary, because those waves carry information. Matthew Hedman and Philip Nicholson, working with Cassini data, showed that some of the waves in Saturn's rings are not driven by moons at all. They are driven by oscillations inside Saturn itself, the planet's interior vibrating at natural frequencies like a bell that has been struck, and those vibrations propagating outward through the planet's gravity and into the rings. The rings respond to Saturn's internal heartbeat. The rings ring, in a sense, and by measuring those waves, their spacing, their speed, their wavelength, scientists can work backward to the oscillations inside the planet that caused them. This field is called chronoseismology, from Chronos, the Greek name for the god the Romans called Saturn, and seismology, the study of vibrations in a body. Chronoseismology. Using the rings of Saturn as a seismograph to read the planet's deep interior. A way of listening to the inside of a world we can never visit, using the ripples it inscribes in its own rings. The idea is beautiful in the way that the best scientific ideas often are, the answer to one question hidden inside the geometry of something else entirely. It is, if you have not already drifted off, a good moment to appreciate that the rings of Saturn are not simply rings, they are a record, a living record of gravitational forces, of moons, of internal vibrations, of the history of the system. Everything that has ever pushed or pulled the rings is written into their structure somewhere, in waves and gaps and wakes and resonances. Cassini spent years learning to read that record. We are still translating it. But there is one more thing happening to the rings that we have not talked about yet. Something that puts everything, the composition, the age, the structure, the spokes still to come, into a new kind of perspective. Because the rings are not just being shaped, they are being consumed. And the rate at which they are being consumed is something Cassini measured with considerable precision in the final months of its life. Here is the thing about the rings and Saturn's magnetosphere. Saturn, like Earth, has a magnetic field, a vast invisible structure extending out from the planet's poles and wrapping around it in great loops. Ring material, particularly the fine dust grains and the molecules of water ice broken apart by solar ultraviolet radiation, can become electrically charged, and charged particles in a magnetic field do not simply float wherever they were. They follow the magnetic field lines. They are guided by them, channeled along invisible tracks, pulled toward the planet's magnetic poles, which in Saturn's case happen to be located roughly at the boundaries between the mid-latitudes and the higher latitudes, at around 30 degrees north and south. And so, charged ring material flows along Saturn's magnetic field lines, down from the ring plane, and falls into Saturn's upper atmosphere. Not metaphorically, literally. Material from the rings is raining down into the planet. This process has a name, and the name is perfect. Ring rain. Ring rain was first hinted at as far back as the early 1980s when instruments on Voyager detected something unexpected in Saturn's ionosphere. the high upper layer of its atmosphere, where solar radiation ionizes gas molecules and creates a region of charged particles. The ionosphere was not uniform. It had dark bands, latitudinal stripes, where the ion density was lower than expected. And those dark bands occurred at specific latitudes. The latitudes where, if you traced Saturn's magnetic field lines upward from the ring plane, they would connect. The ionosphere was being suppressed locally at exactly the spots where the magnetic field reached down from the rings. It took decades to fully understand what that meant. James O'Donoghue, working later with data from the Keck Observatory in Hawaii, confirmed and measured the phenomenon with much greater precision. The infalling ring material, water in various molecular forms, it was suppressing Saturn's ionosphere where it fell, chemically altering the upper atmosphere. The rings were reaching down and touching the planet, invisibly, through the conduit of the magnetic field. But it was Cassini's grand finale that changed everything. In those final orbits, flying through the gap between the innermost ring and the top of Saturn's atmosphere, Cassini's instruments could sample directly what was flowing in that gap, what was actually raining downward, and the measurements were startling. The combined infall of ring material, ring rain from the magnetic funneling, plus additional material that simply crosses the ring plane and drifts inward under various forces, was coming in at a rate of up to roughly 10,000 kilograms per second. 10 metric tons of ring material every single second disappearing into Saturn. Sit with that for a moment if you can. 10,000 kilograms per second. In the time it takes to breathe in and breathe out, another 10 tons of Saturn's rings have ceased to exist as rings and have become part of Saturn itself. Every minute, 600 tons. Every hour, 36,000 tons. Every year, the rings lose hundreds of billions of tons of material to this process alone. And you can see immediately what this means. If the rings are losing material at this rate, they cannot last forever. The question is how long they have left. James O'Donoghue and his colleagues worked through the math, comparing the measured infall rate with estimates of the total mass of the rings. That mass we calculated from Cassini's gravity measurements, roughly 1.5 times 10 to the 19th kilograms, less than half the mass of Mimas. And the answer that came back was not a comfortable one if you are the kind of person who was hoping Saturn's rings might be a permanent feature of the solar system. At current loss rates, the rings have somewhere between roughly 100 million and 300 million years remaining. Some estimates push the number toward the shorter end of that range. Some are a little more generous. The uncertainty is real, and the debate about ring age and ring lifetime is not a settled one, but even the most optimistic estimates put the ring's remaining lifetime well within a few 100 million years. On a human timescale, that sounds vast. On a geological or astronomical timescale, it is a blink. The rings are dying. Slowly, imperceptibly, drain by drain, they are losing themselves to Saturn. What looks from a distance like something permanent, those luminous arcs that have defined Saturn's image in every telescope since Galileo first squinted at it through his crude lens, is actually an ephemeral structure, a transient, a thing that happened, is happening now, and will one day be gone. And remember, the rings are also young, not just dying, but young. They formed perhaps 100 to 400 million years ago, which means they have already lived somewhere between 1/3 and 2/3 of their total lifespan. The Saturn we would have seen from Earth 200 million years ago would have looked different, and the Saturn that any civilization alive in another 200 million years might observe would look different again, perhaps ringed still, but more faintly, with thinner, sparser bands. And the Saturn of 1 billion years from now? The rings may well be gone. We are watching them in their middle period. They're flourishing. their moment of greatest drama and complexity. And we are among the first beings anywhere to understand what they are and to measure how quickly they are fading. There is something in that which asks to be felt rather than just noted now. Cassini's instruments during those final orbits did not just measure how much material was falling into Saturn, they measured what that material was, and here the story takes another turn, because the answer was more complicated than anyone had expected. The obvious answer, the one you would assume if you had heard that Saturn's rings are roughly 90 to 95% water ice, is that what rains down into Saturn is mostly water. Water molecules, water ice grains, hydroxyl molecules from water broken apart by sunlight. And yes, water was there. Water was a major component of what Cassini's instruments, particularly the ion and neutral mass spectrometer, the INMS, tasted in the gap between rings and planet. But it was not the only thing. The INMS data, published by J. Hunter Waite and colleagues in 2018, revealed a chemical cocktail that nobody had fully predicted. Along with the water, there was methane, there was ammonia, there was carbon monoxide, there was molecular nitrogen, there were silicate nanoparticles, tiny grains of rocky material, the stuff of stone raining down alongside the ice. This is worth pausing over. The rings, remember, are almost pure water ice, 90 to 95%. The remainder is a small fraction of rocky and carbonaceous material. And yet the infalling material sampled in the gap had a notably more complex chemistry than the bulk ring composition would suggest. The ring rain is not simply a slow drip of the ring's average composition down into Saturn. There are processes at work: sputtering by energetic particles, photodissociation by sunlight, chemical reactions in the plasma environment, the selective transport of different species along magnetic field lines that produce a richer, stranger mixture than the ice alone. The rings, as they dissolve into Saturn, are exhaling something complicated, not just water, a cocktail of molecules that will alter Saturn's upper atmosphere, mix into its chemistry, become part of the planet in ways we are still working out. The rings are not simply disappearing, they are becoming Saturn. Slowly, molecule by molecule, they are rejoining the world that, in a sense, they came from. Because that is the other side of the loss. The rings formed from Saturn's material, or from material in Saturn's orbit, a moon shredded, a comet captured, and now they are returning, grain by grain, into Saturn's atmosphere. A circulation, a slow dissolution. The ring system as something that arose and is now, on cosmically long timescales, folding back in. Waite and colleagues published that result, the chemical cocktail, in the grand finale gap data, in the journal Science in 2018, alongside several companion papers from other Cassini instrument teams that collectively painted the same picture. The space between Saturn's rings and its atmosphere is not empty, and what moves through it is not simple. The grand finale was not just a way to end the mission without contaminating any of Saturn's moons. It was a scientific opportunity that could only have been taken by a spacecraft willing, or rather directed, to fly where no probe had ever flown before, through a gap that had been considered too risky to enter for the entire previous mission, reserved for the very end, and the ionosphere. Remember the dark bands Voyager saw in the early 1980s, the strips of suppressed ionosphere at specific latitudes, the first hint that something was flowing down from the rings. O'Donoghue's later work with Keck, and then the Cassini in situ measurements confirmed that those bands are the footprints of ring rain on Saturn's atmosphere, the places where infalling ring material quenches the local ionosphere, chemically neutralizing the charged particles and reducing the ion density. The rings are writing themselves on Saturn as they pour into it, leaving their mark in the atmospheric chemistry, in those bands in the suppressed glow of Saturn's ionosphere, at the latitudes where the magnetic field lines connect from ring plane to planet. It is one of the stranger closed loops in the solar system. The rings, born from material that may have orbited Saturn for billions of years, take their current form perhaps 100 million years ago. They orbit and scatter light and draw the eyes of every being that has ever looked up at the sky with a good enough instrument. And then, quietly, they drain, they rain, they fall back into the planet, leaving faint chemical shadows in the ionosphere as they go, and eventually they will be gone. All of that, the propeller moonlets named for aviation pioneers, the shepherd moons with their ravioli shapes, and their kilometer-long wave shadows, the restless braided F-ring needed by Prometheus, the density waves that carry Saturn's internal heartbeat outward into the ring material and let us read the planet's deep interior, and now the ring rain, the slow bleeding of the rings into Saturn at 10,000 kilograms per second, the chemical cocktail of water and methane and ammonia and silicates and molecular nitrogen flowing down the magnetic field lines into the planet's upper atmosphere. All of that is what is actually happening inside and around the rings right now, as you lie wherever you are listening, as your eyes grow heavy or perhaps stay bright. All of it is happening out there in the cold dark of the outer solar system, continuously, whether anyone is watching or not. But there is one more thing. One piece of the story that we have been circling around since the very beginning. The thing that perhaps drew you here in the first place, or that at least should have. The feature that earned the name we gave it, that appeared without warning in Voyager's images, that waxes and wanes with the season, that can stretch to the size of Earth across the B-ring's face, and that, after more than 4 decades of observation and modeling and debate, still does not have a fully confirmed explanation. The spokes have been waiting, and they deserve the full attention that is coming to them. So let us give it to them. When Voyager 2 swept past Saturn in 1981, the imaging team was looking for detail. They expected structure, resonance gaps, wave patterns, the fine architecture they had come to anticipate from the earlier Voyager 1 flyby. What they did not expect, and what the images delivered anyway, were dark, radial streaks sprawling across the face of the B-ring like shadows painted by an enormous spinning wheel. They were not gaps, they were not waves, they were not consistent with anything orbiting particles should do. Particles in a ring obey Kepler's laws. The inner ones move faster than the outer ones, so any feature that started out radial should shear apart within hours, smearing into a spiral and then into nothing. The streaks should have been impossible, and yet there they were, thousands of kilometers long, persisting. The team named them spokes. That name stuck because it was exactly right. Look at a bicycle wheel from the side and you see the spokes radiating outward from the hub, evenly, rigidly, all at the same angle. Saturn's spokes look like that. Except the hub is Saturn itself, and the spokes are not rigid. They form, they last, for a matter of hours, and then they dissolve back into the ring material as though they were never there. And then new ones form, and the whole cycle begins again. The first thing you notice if you think about this carefully is that something must be making those dust particles move together. Not shear apart, but stay coherent. In a ring system governed by gravity alone, that is simply not possible for a radial feature. Gravity does not do that. Gravity does exactly the opposite. So whatever is holding the spokes together, at least temporarily, is not gravity. It is something else. And the leading candidate, the mechanism most planetary scientists find most plausible, involves electricity. Here is the basic idea. The ring particles, the billions of small ice and dust grains that make up the B-ring, are not floating in a vacuum that is entirely empty and neutral. They are embedded in Saturn's magnetosphere, a vast invisible envelope of magnetic field and plasma that rotates with the planet. When something disturbs the ring locally, a micrometeoroid impact, for instance, a tiny piece of interplanetary dust striking the ring surface and vaporizing in an instant, it releases a cloud of plasma, a brief burst of electrically charged gas. The finest dust grains in the vicinity, the ones tiny enough to be affected, pick up an electrical charge from that plasma. And charged particles in a magnetic field do not just sit there, they respond to the field. They can be levitated, lifted slightly off the ring plane, decoupled from the purely gravitational dance that governs their heavier neighbors, and swept along at a speed that matches the rotation of Saturn's magnetosphere rather than the Keplerian speed appropriate to their orbital position. And that is the key. Saturn's magnetosphere rotates with the planet. Saturn itself rotates in roughly 10.5 hours. But the ring particles at the B ring's distance orbit more slowly than that. The outer parts of the B ring take longer than Saturn's own rotation period to complete a single circuit. So a dust grain that gets levitated and starts moving with the magnetosphere is suddenly moving faster than its neighbors. It sweeps outward, or it follows the field lines, and the result is a coherent radial structure, a spoke, maintained not by gravity, but by electromagnetic force, by the planet's spinning magnetic personality, reaching down into its own rings and briefly reorganizing a strip of fine dust into something that looks, from a camera millions of kilometers away, like the shadow of a clock hand. It is a beautiful mechanism, and it is probably largely correct, but here is the honest part of the story, the part that makes the spokes genuinely interesting rather than merely described. No one has confirmed it in full detail. The dusty plasma model, the electrostatic levitation framework, captures the essential physics of why something radial and coherent could form in a differentially rotating ring. But the specifics, the exact triggering conditions, the precise plasma densities required, the question of why spokes form in some places and seasons and not others, why they seem to cluster near a particular region of the ring, why they scale in intensity the way they do, these details are not nailed down. The spokes remain, after 44 years, an open problem at the frontier of planetary science. Not a complete mystery, not an alien phenomenon beyond understanding, but genuinely, honestly, not yet fully solved. And the seasonality is perhaps the most intriguing part of that unfinished picture. Saturn takes just under 30 years to orbit the Sun, 29.5 Earth years. That means its equinoxes, the moments when the Sun crosses the ring plane and sunlight strikes the rings nearly edge-on, come roughly every 15 years. And the spokes are tied to those equinoxes. They strengthen as Saturn approaches its equinox, growing more frequent and more vivid, and they fade as the planet moves away toward its solstice, when sunlight falls steeply on the rings, and the geometry is entirely different. Cassini watched this happen in real time. As the 2009 equinox approached, the spokes returned and intensified, behaving exactly as the seasonal pattern predicted. Then, as Saturn moved on in its orbit, they quieted again. Why would sunlight geometry affect an electromagnetic phenomenon? That is part of what remains unresolved. One idea involves the way ultraviolet light from the Sun charges the dust grains differently depending on angle of incidence. Edge-on sunlight may charge the grains more efficiently, or may alter the local plasma environment near the ring in ways that make levitation easier. Another idea connects the seasonality to the shadow the rings cast on Saturn's upper atmosphere, which affects the ionosphere, which feeds back into the magnetosphere, which eventually changes the conditions at ring level. The connections are real. The precise causal chain is still being worked out. What we do know is this. Right now, as you are listening, Saturn is approaching its 2025 equinox. The rings are tilting edge-on to our line of sight from Earth, which is why they will appear to almost vanish from telescopes over the next year or so, presenting that famously puzzling profile that confused Galileo 4 centuries ago when they disappeared entirely for months in 1612. And precisely because it is equinox season, the spokes are coming back. Hubble Space Telescope, through the Outer Planets Atmospheres Legacy Program, the OPAL program, has been imaging them. The James Webb Space Telescope has turned its extraordinary eye towards Saturn specifically to catch them in this window. There is no spacecraft at Saturn right now to watch up close, the way Cassini did. So the monitoring falls to our best telescopes at Earth, doing what science does when the proximity data runs out, watching carefully from a distance, recording what the changing light reveals, and waiting for the pattern to yield something new. The spokes are being watched, right now, in the same weeks and months that you are hearing these words. And that, in a way, is the right note on which to hold for a moment. Not to resolve it, because it has not been resolved, but to sit with the fact that the most famous unexplained feature in Saturn's rings is not a historical puzzle tucked away in old papers. It is a living observational question that active astronomers are actively pursuing with the most capable instruments humanity has ever built, pointed at a planet that has kept this one particular secret for longer than most people alive today have been alive. And so let us return, now, to the spokes themselves. Let us sit with them a little longer because they deserve it, and because after everything we have moved through, the composition, the age, the hidden moonlets, the shepherd moons, the chemical cocktail raining into Saturn's clouds, the spokes are the thing that earns the word mystery without any qualification at all. You remember what they are, roughly. Ghostly radial markings like the spokes of a very ancient and very strange wheel appearing across the surface of the B-ring. Stretching sometimes as much as 20,000 kilometers in length and roughly 2,000 kilometers wide, features the size of Earth written in faint dust across the face of a ring system that is, let us recall, only about 10 meters thick. They are vast in 2 dimensions and impossibly thin in the third, and they appear and they vanish over the course of minutes to hours, and no one has ever fully explained them. But we can say some things about what they are made of, even if we cannot yet say with confidence why they form. And the optical signature is where that understanding begins. When the Voyager cameras captured the spokes and when Cassini spent years studying them, scientists noticed something immediately telling about the way light behaved around them. If you look at the spokes with the sun behind the camera, the light bouncing off the ring material back toward the observer, what astronomers call backscatter, the spokes appear darker than the surrounding ring. The ring glows and the spokes shadow it. But if you reverse that geometry, if you look at the spokes with the sun on the other side, lighting the material from behind, forward scatter, the light passing through, suddenly the spokes glow brighter than the ring around them. They become luminous, almost translucent. That particular reversal, dark in one direction, bright in the other, is deeply diagnostic. It tells you something very specific about the size of the particles doing the scattering. Ordinary ring particles, the centimeter to meter, snowballs and boulders that make up the bulk of the B-ring, scatter light quite differently. But particles in the micron range, grains smaller than the thickness of a human hair, fine as the particles in cigarette smoke or in high-altitude cloud, those scatter forward particularly well. They glow when the light comes through them. The bright forward scatter of the spokes means that whatever is making them visible is extraordinarily fine, micron-sized dust, almost impossibly small. And now the geometry becomes puzzling in a new way. If you have fine dust sitting in the ring plane mixed in with the regular ice particles, you would not necessarily see it as a distinct feature. The ring is too dense, too thick in particle traffic for a trace of micron dust to stand out at all, but the spokes do stand out. They appear above the ring, not just in it, or rather, their optical properties are consistent with material lofted above the ring plane, floating in the space just over the dense sheet of ice, catching light differently because it is separate and elevated and fine. So the question immediately becomes, what could lift micron-sized dust particles up off the surface of a ring system and hold them elevated? And here is where electrostatics enters and where the story gets genuinely strange. The leading explanation, and it remains a model, a well-supported hypothesis, not a confirmed mechanism, involves Saturn's magnetosphere and the electromagnetic properties of charged dust. Saturn has a powerful magnetic field rotating with the planet. The ring particles in the B ring are orbiting on their own Keplerian trajectories, at speeds governed by gravity. But the magnetosphere is rotating at Saturn's own rotation rate, which is different. Where the magnetosphere's co-rotation speed and the ring particle's orbital speed diverge, you get a relative motion between the ambient plasma and the solid ring material. Now, if a dust grain is very small, small enough that its surface area is large relative to its mass, it can acquire an electrical charge. It does this by interacting with the plasma environment, ions and electrons in the magnetosphere impinging on the grain, ultraviolet light from the sun knocking electrons loose from its surface. A grain that becomes electrically charged in a region with a magnetic field will experience a Lorentz force, the electromagnetic push that bends the paths of charged particles. And if the grain is small enough, if its mass is tiny enough, that the electromagnetic force exceeds the gravitational pull trying to keep it in the ring plane, the grain can be levitated, lifted off the ring, suspended above it. This is what physicists call a dusty plasma, not a conventional plasma of pure ions and electrons, but a system where solid charged grains participate in the electromagnetic dynamics, behaving in ways that ordinary uncharged matter would not. The rings in the regions where spokes form may be briefly behaving like a dusty plasma, a charged, levitating fog of micron grains held above the B ring by electromagnetic forces tied to Saturn's magnetic field, glowing in forward scattered light like a luminous shadow. It is a beautiful idea, and it is partially supported by the observations. The spokes do appear to form in regions where the magnetospheric rotation rate most closely matches the ring orbital rate, near the synchronous orbit radius, the particular distance where ring particles orbit at exactly the same speed as Saturn rotates. That is suggestive. It hints at a real magnetospheric connection. But there is a step that remains unconfirmed. Something has to trigger the initial charging event. Something has to abruptly charge the grains and lift them in the first place. One candidate is the micrometeoroid, a tiny piece of interplanetary debris, no larger than a grain of sand, striking the ring at high speed and releasing a brief burst of vaporized material and ions, a small plasma cloud. In that cloud, the local electromagnetic environment would briefly change, grains would charge, and a lofted spoke might begin to form and spread. The expanding spoke would then follow the ring material's orbital motion, stretching and shearing over time into that characteristic radial smear before the grains gradually lose their charge, fall back into the ring plane, and the feature fades. It is a plausible story. It is consistent with the timescales, minutes to hours, over which spokes are observed to form and dissipate. It is consistent with the location and the particle sizes, but it has not been confirmed. The exact trigger has never been caught in the act. No one has definitively watched a micrometeoroid strike, watched the plasma cloud bloom, and watched a spoke form in response. The spoke mechanism remains in the category of well-reasoned inference, not finished science. And there is at least one more layer of mystery on top of that, which is the seasonal behavior, because if the spokes were simply triggered by random micrometeoroid strikes, you might expect them to be present all the time, more or less uniformly, scattered across the B ring whenever debris happens to fall. But they are not like that. They are seasonal. They come and go on a clock tied to Saturn's relationship with the Sun, not to any random impact schedule. Cassini watched this over its 13 years at Saturn. When it arrived in 2004, close to Saturn's northern summer solstice, the spokes were rare. Cassini's cameras searched and found them only occasionally. But as Saturn moved through its orbit, as the years passed and the Sun's angle above the ring plane slowly decreased toward the 2009 equinox, the moment when Saturn's rings would appear edge-on from Earth, when the Sun would cross from one hemisphere to the other, the spokes became more frequent, more prominent, more vivid. They returned. Saturn's year is roughly 29.5 of our own years. An equinox, a crossing of the ring plane by the Sun, happens twice in each Saturn year, which means roughly every 15 years from our perspective. Near equinox, the sunlight strikes the rings at an extremely shallow, low angle. Near solstice, it strikes from high above or below the plane. The geometry changes what the Sun does to the ring environment, how much ultraviolet light hits the particles, how much the particles charge, how the electromagnetic balance between photoelectric charging and plasma environment charging shifts. Near equinox, that balance apparently tips toward conditions where spokes form more readily. Near solstice, conditions are less favorable and the spokes retreat. Exactly why that geometric shift promotes spokes so strongly is itself not perfectly understood. The seasonal correlation is observed. The mechanism connecting solar geometry to spoke formation is still being worked out. So the spokes carry a mystery within a mystery, not just what are they, but why do they depend on the season? What this means in practical terms is that right now, as you hear these words, Saturn is in its spoke season. The 2025 equinox is approaching, and because no spacecraft is currently orbiting Saturn, Cassini made its final dive in September 2017, plunging into the planet's atmosphere, gone. The only instruments watching are the ones we have on Earth and in Earth's orbit. The Hubble Space Telescope, through the Outer Planets Atmosphere's Legacy program, has been trained on Saturn specifically to document the spokes in this window. The James Webb Space Telescope, with its extraordinary infrared sensitivity and its ability to resolve fine detail in Saturn's ring structure, has also joined the campaign. Teams of planetary scientists are, at this moment, processing images, comparing spoke frequency, measuring spoke dimensions, looking for patterns in when and where the features form that might finally yield the additional clue the mechanism needs. This is what active science looks like. Not the version from history books, the clean retrospective where everything was figured out and the names are already on the equations. The alive version where people are sitting at workstations in universities and research institutions, looking at images of a planet 1.5 billion kilometers away, making careful measurements, writing code to pull signal from noise, arguing with each other at conferences about what the data is really saying. The spokes are a live puzzle being actively pursued, and the pursuit is happening right now during the same window in which you are hearing this. There is something quietly remarkable about that coincidence of timing. Roughly every 15 years, the conditions are right. In between those windows, the spokes retreat and the urgency fades. But the window is open and the telescopes are looking. Now, the spokes are not the only sense in which Saturn's rings are alive and active. There is another dimension to that aliveness, one that connects the rings not just to the space around Saturn, but to the planet far below. You will recall from earlier in this journey the story of the Enceladus geysers, the discovery that Saturn's icy moon, Enceladus, just over 500 kilometers across, is erupting constantly from its southern pole. Cracks in the ice there, called tiger stripes, vent enormous plumes of water vapor and ice grains and complex organic molecules into space. It is a dramatic piece of geology for a small moon, driven by tidal heating from Saturn's gravity, needing the moon's interior. And what those plumes do is feed the rings. The E ring, the large, diffuse outermost of the main ring family, extending far beyond the narrow and dynamic F ring, is sustained by material from Enceladus. The Moon orbits within the E ring, and its eruptive plumes continuously refresh the fine, icy particles that would otherwise gradually disappear. The E ring is not a relic. It is being actively maintained by a living geological process on a moon below it. The rings and the moons are not separate systems. They are connected in a conversation of gravity and ice and outgassing that runs continuously. And there is another ring at the far outer edge of Saturn's family that has a story of its own. The Phoebe ring is enormous, vastly larger in extent than all the bright inner rings combined, tilted at an angle relative to the ring plane, oriented differently, made of dark material rather than bright ice. It was discovered in 2009 by the Spitzer Space Telescope, which observed its heat signature. The Phoebe ring is fed not by geysers, but by the dark, distant moon Phoebe itself, orbiting far out in a retrograde, tilted path, a captured irregular satellite, most likely a body that came from the outer solar system long ago and was snared by Saturn's gravity. Micrometeoroid impacts on Phoebe's surface knock dark dust off into space, and that dust gradually spirals inward, forming this vast and dim outer ring. So at one end of the ring system, a small erupting moon is building ice rings. At the other end, a dark, captured moon is shedding debris into a ring tilted against the grain. The rings are not one uniform system. They are a collection of different histories, different materials, different sources accumulated around one planet. And it is worth pausing for a moment on the fact that human beings did not always know any of this. For centuries, the rings were a beautiful and deeply puzzling observation, something no instrument was powerful enough to fully explain, and something that required centuries of accumulated understanding to begin to read correctly. The story begins with Galileo Galilei in 1610 turning one of the earliest telescopes towards Saturn. His instrument was good enough to show him that Saturn was not simply a round disk the way the other planets appeared, but it was not good enough to show him what was actually there. What he saw looked to him like Saturn was accompanied by two smaller bodies, one on each side, pressed close to it. He described the planet as appearing to have ears, or as a triple body. He wrote of it as though the planet were flanked by companions. He did not understand what he was seeing. And then 2 years later, in 1612, he looked again, and the ears had vanished. Saturn was alone, a perfectly round disk, unaccompanied, as plain as any other planet. Galileo was genuinely confused. He wrote that he did not know what to say about a thing so strange. He worried, it seems, that he had been wrong or deceived, or that the planet had consumed its companions. What had actually happened was a ring plane crossing. Saturn's rings had tilted edge-on to the Earth, and at that angle, at the resolution his telescope could achieve, they simply disappeared. They were too thin to see. He had watched something extraordinary vanish and had no framework with which to understand it. That absence is that puzzling blankness where the ears had been is actually one of the earliest data points in the long history of figuring out what Saturn's rings are. Decades later, in 1655, the Dutch astronomer and mathematician Christian Huygens, working with a better telescope and a sharper mind applied to the problem, correctly identified what he was seeing. He described Saturn as being surrounded by a thin, flat ring, nowhere touching, inclined to the ecliptic. That phrase, thin, flat ring, nowhere touching, was the breakthrough. Not spheres, not moons, not a physical extension of the planet. A ring, separate, flat, surrounding the planet at a distance. Huygens was right, and the framework he provided began the long process of understanding what the ring actually was. And then 2 centuries after Huygens, in 1859, James Clerk Maxwell, a Scottish physicist who would later give the world the equations unifying electricity, magnetism and light, turned his attention to a mathematical question about Saturn's rings as a prize problem, the Adams Prize at Cambridge. The question, could the rings be solid? Could they be liquid? What must they be? Maxwell proved rigorously that a solid ring could not remain stable. Gravitational forces would tear it apart or torque it into instability, and it would break. A liquid ring was similarly unstable. The only configuration that was physically stable, that could persist without being destroyed by its own internal dynamics and by Saturn's tidal forces, was a ring made of countless separate, independently orbiting particles. Uncountable individual pieces, each on its own path around the planet, collectively giving the impression of a continuous sheet. It was a theoretical prediction made before the instruments existed to confirm it directly. And it was confirmed in 1895 by the astronomer James Keeler, who measured the Doppler shift of light from different parts of the ring. If the rings were solid, every part would rotate at the same rate, the way a spinning coin rotates. But Keeler's measurements showed that the inner edges of the rings were moving faster than the outer edges, exactly as Kepler's laws of orbital motion predict for independently orbiting bodies where inner orbits are faster. The rings were not solid, they were a swarm. Maxwell had been exactly right. These moments, Galileo's confusion, Huygens's clarity, Maxwell's proof, Keeler's confirmation, form a kind of slow accumulation of understanding across centuries. Each step using better instruments, better mathematics, sharper reasoning, to peel back another layer of what the rings actually are. And here we are, 4 centuries after Galileo wrote about ears and mystery. We have sent spacecraft through the rings, measured their mass by feeling their gravity, tasted their chemistry as they rain down into Saturn's atmosphere, watched hidden moonlets carve propeller wakes, tracked shepherd moons raising waves hundreds of meters tall, and identified an active erosion process draining tons of material into the planet every second. And we still cannot fully explain the spokes. There is something very human about that. The way understanding accumulates slowly, never quite catching everything, always leaving one mystery unsolved even as another closes. The spokes are not a failure, they are the thing that is left when you have done the hard, patient, rigorous work of explaining everything else, and they represent the frontier, the genuine edge where knowledge runs out and observation and hypothesis are still negotiating with each other. Let us zoom out now. Let us take the whole picture and hold it at arm's length for a moment. Saturn's rings stretch nearly 282,000 kilometers across, a span that would swallow more than 20 Earths placed side by side, but they are 10 meters thick. 10 meters. The ratio is so extreme, it reads almost like a typographical error. Across the width of a city, and we are talking about a span far wider than any city, wider than most countries, the rings are no deeper than a 2-story building. A sheet of paper scaled up to the size of a continent would be thicker in proportion. They are, in that sense, the flattest large thing in the known solar system. And they are almost perfectly white. 90 to 95% water ice, pure enough to be suspicious. The kind of purity that tells you these rings have not been accumulating cosmic pollution for billions of years, because if they had, they would be dark by now. The micrometeoroid dust that rains in from space is dark, carbonaceous, a constant slow dye that any sufficiently old ring would have absorbed. The rings are bright because they are young enough that the contamination has not yet had time to stain them. We live at an unusual moment. The rings are perhaps 100 to 400 million years old. The age of the dinosaurs stretches from roughly 230 million to 66 million years ago. The rings may have formed while dinosaurs were walking the Earth. They may have formed before the very first dinosaur species emerged. They were not there when life first appeared. They were not there when the oceans formed. They are a recent feature of a very old planet, and they will not last forever. At the measured rate of ring rain, up to around 10,000 kilograms per second draining down into Saturn's atmosphere along magnetic field lines. The rings have somewhere in the range of 100 to 300 million years left, perhaps shorter. The machine is running, and the machine is losing material constantly, and eventually the reservoir will empty. We are watching them during a window, a privileged interval in Saturn's history, when the rings are bright and full and spectacular. Our descendants, millions of years from now, should there be any watching from Earth, will see a different Saturn. Dimmer rings, thinner rings, eventually no rings at all. Just the planet itself, unadorned, the way it looked for the first 4 billion years of the solar system's life. The rings are not permanent, they are not ancient, they are not fully understood, and they are actively dying, and yet in this moment, in this season, with the Sun crossing the ring plane and the spokes returning, with Hubble and Webb watching from their perches in Earth's orbit, with planetary scientists processing images and writing papers and arguing about charging mechanisms and magnetospheric dynamics. In this moment, the rings are doing something no one can quite explain, and they are doing it in full view of our best instruments. Think about where you are right now as you hear these words. Wherever you are, lying in bed in a city or a town or somewhere quiet, a lamp perhaps still on, or the room fully dark, the night outside doing whatever the night does where you are. Above you, further than any distance that makes intuitive sense, Saturn is there. Its rings are tilted toward the edge-on, presenting that narrow profile that confused Galileo. And somewhere in the B ring, the widest and brightest and most massive of those rings, ghostly radial features are forming and fading. They are doing it right now in real time, on a time scale of minutes to hours. Earth-sized structures made of micron-sized dust, electrostatically charged, briefly defying gravity, glowing in scattered sunlight, and then settling back. They were doing this before the Voyager cameras caught them in 1981. They were doing it before Maxwell proved the rings had to be particles in 1859. They were doing it in 1612 when Galileo watched, baffled, as the entire ring system seemed to vanish. The spokes have been forming and fading across the B ring for as long as the rings have existed, which is, we think, about as long as there have been dinosaurs on Earth, give or take. No one has been watching for most of that time. No one had instruments capable of seeing them until 40-some years ago. And even now, with everything we have built and launched and aimed at Saturn, the full explanation still eludes us. There is a kind of comfort in that, I think. Not the comfort of resolution, but the comfort of a universe that is genuinely and persistently stranger than it first appears. Every time the image of Saturn's rings seems complete, every time you feel you have it, the wide, flat ice disk around a giant golden planet, something adds another layer. The rings are young. They are draining. They have moonlets hiding inside them you cannot see. They have ghosts the size of Earth flickering in and out of existence. The familiar picture keeps deepening. Back at the very beginning of our evening together, I asked you a question, or really, I asked the title ask it for us. What is actually inside Saturn's rings? The hope, maybe, was for a tidy inventory. Ice and rock, we knew that. But we wanted to know what else. What is actually in there? And the answer turned out to be more than ice, and more than rock, and more than a list of ingredients could carry. Inside Saturn's rings there is a history of a lost moon, perhaps shredded by tides 150 million years ago, whose debris became the bright particles we can see from Earth. There is a dynamic of moonlets ploughing through ice, of shepherd moons raising waves, of electromagnetic forces lifting dust. There is a chemistry of charged particles draining down magnetic field lines, of methane and ammonia and silicate nanoparticles falling into a planet's upper air. There is a clock ticking at the rate of tons per second, counting down toward a Saturn without rings. And there is a mystery, unreduced, genuine and ongoing, of radial spokes that form with the seasons and vanish in ways the best models we have do not yet fully account for. What is actually inside Saturn's rings, it turns out, is a question that science has spent centuries refining and is still in the process of answering. And right now, in this equinox window, with the best instruments humanity has ever assembled, watching carefully, the answering continues. I hope this slow drift through it gave you something to carry into the quiet. The rings of Saturn are not what they look like at first, not a static halo, not an eternal ornament. They are a brief and complicated and beautiful machine running on ice and gravity and electromagnetism and time, and they will not be there forever. We are fortunate to be alive in the window when they are. And you, wherever you are in the world tonight, are made of the same atoms that built those rings. The water in the ring particles and the water in your body share the same ancient origin, scattered across the solar system 4.5 billion years ago in the cloud of gas and dust from which everything formed. Saturn's rings are almost entirely water ice. You are more than half water. There is a version of the story in which you and those rings are the same material, separated by distance and time, and the particular arrangements that made some water into snowballs orbiting a gas giant, and some water into a person lying in bed, listening to the night. That is not a bad thing to carry gently into sleep. If you have found some pleasure in this long, slow walk through the rings, a like and a gentle subscription to Orbit Observer means more than you might think. Small creators like me truly do rely on your support to keep these journeys going. And if you have a moment before sleep takes you, I would love to know where in the world you are listening from tonight and what time it is in your corner of the dark. Leave it in the comments if you like. I do read them. The spokes will keep forming and fading. Hubble and Webb will keep watching. And the answer, when it comes, will be one more layer under the answer that came before. Good night from up here in orbit. I'll keep watch while you drift.